Okay, so in this video, we're going to have a look at proof by contradiction. So previously we've covered proofs before. This particular style of proof is basically taking a statement and assuming the opposite is true and finding that you can't actually prove that statement is true. So for example, if we start with the statement, if n squared is even, then n must be even. We're going to start by writing down what we're going to call the assumption. So our assumption here is that if n squared is even, then n must be odd. So we're just going for the exact opposite of what's given. So if n squared is even, then n must be odd. So we're going to start with n being odd, and we're going to find out what happens to n squared and go from there. So if n needs to be odd, then we're going to let n equal 2k plus 1. So some kind of standard kind of format for an odd number. If n is 2k plus 1, then we obviously want to find out what n squared is. So n squared is equivalent of 2k plus 1 all squared, and that is equal to 4k squared plus, and then 2k times 1 is 2k. Double that up for the two brackets, get 4k, and then plus 1. Factorizing this one, I'm going to take 4 out where I can, and I can only take 4 out of these two. Technically speaking, actually, I'm going to take 2 because I want to show it's even, and we know that any even number is just 2 times something. So rather than 4, actually, I'm going to take a 2 out, just to show what's going on here. So I've got 2 times, now I've got this 2k squared plus 2k, and then I've got plus 1. I don't know why I'm choosing to do my ones slightly differently. This is 2 times something plus 1, so this is actually odd, because this first part's even plus 1 is odd, and therefore that's not showing us that n squared is even. So if n is actually odd, then n squared is odd, which is basically the opposite of what we wanted to show. So we just need to kind of put that down here. So n squared is odd, and this contradicts our assumption that n squared would be even. So our assumption was that n squared is going to be even and n must be odd. So this is a contradiction. So I'm just going to put n squared is odd, which contradicts the assumption that n squared is even. And that's all I kind of wanted to say for that. Same idea for root 2. I find these ones slightly trickier because it's to do with rational numbers. First thing I want to talk about is what a rational number actually is, or irrational numbers. So a rational, rational, this is any number that can be written as a fraction, so a over b. So if a number is rational, we can write it as a fraction, and if it's irrational, we can't write it as a fraction. So our assumption here is that we can take some number, root 2, and that we should be able to write it as a fraction. So here where we want to prove by contradiction that it is an irrational number. So our assumption here is going to be that it's not an irrational number, or in other words, it is a rational number. So our assumption is root 2 is a rational number. So we're just going for the direct opposite of what was originally stated. So if this is true, this means that root 2, therefore, can be written as sum a divided by b for some kind of numbers a and b. So whatever they might be. So for some a and b. We could also assume that a over b, this is its simplest format. So obviously, if I wanted to write a over b, it might be that a is a multiple of b. I'm going to assume here that this is in its simplest format and that a over b is as simple as it can be. So what I'm going to do here is I'm just going to square both sides. So I get therefore, or implies that 2 must be equal to some a squared divided by b squared. So I've squared up the left-hand side and I've squared up this one, which implies that 2b squared is equal to a squared. So 2b squared, so times in through there, is equal to a squared. So this therefore means that a squared must be divisible by 2. But if it's divisible by 2, then that means we can write as an even number. So let's just get this on paper first of all. So this must mean that a squared is even, so a must be even. So this implies, so stop using the implication sign as much. So a squared is even, which means, and this isn't implies, that a must also be even. So that's what we can kind of deduce from this part. So this now means that if we can, if a is even, we can write as 2n or 2k or something, which ultimately, this first step is going to be the one that falls down. So where I said that a over b, that there's going to be no common factors. So I didn't actually write that. So I should, let me just make that explicit because that's going to be the crux of this. So where a over b is fully simplified, it's going to be this bit that I'm going to show that this is not actually true. So when I get a over b, I'm going to show that there's another factor that it kind of cancels again, which kind of breaks the whole system. So if a is even, that means I can write a as, let's say, some 2 times k. If a is 2k, then what is, let's say, a squared? That must be 4k squared. And if I know what a squared is, I know what b squared is because it's just double that. So therefore, b squared is going to be whatever this is, kind of times by 2. So a squared is, actually, it's going to be divided by, either way. Just using this formula here, I'm going to put this in here and just divide. So this means that basically 2b squared is equal to 4k squared. So b squared is equal to 2k squared. So that's that last little bit there. So b is also even here, which is a little bit counterintuitive because it means we can simplify. If both these numbers were even, why would we not be cancelling down? And that's going to be the contradiction here. So here we've got that b is also even. So if a was even and b was even, we'd have been able to simplify this further. That is a contradiction because right at the start, I said it's fully simplified. So therefore, root 2 must be in an irrational number because we've got this contradiction. So if a and b are both even, then a over b could be simplified, but they have a common factor there. So it would simplify further. Then and that's going to be a contradiction. And we're just going to keep going around in circles like this, unfortunately. So that's it. So it's a contradiction at our earlier statement. So therefore, root 2 is irrational. Now, I would definitely recommend that you go through every single one of these questions in the book. There's not loads and loads of them. They're non-calculated for the most part. But yeah, it's basically just going through logical steps to show that this can't happen. I'm going to do one more. And it's use proof by contradiction to show that there exists no integers a and b for which 21a plus 21b, 21a plus 14b equals 1. So I'm just going to write that out to start with. Obviously, contradiction here is that there's no integers. So I'm going to assume that there are integers. So my assumption here is that there are integers. So my assumption here is there exists an a and b for which 21a plus 14b is 1. So there exists an a and b such that 21a plus 14b equals 1. And it's a and b which are integers. So I'm just going to make that clear here, but where a and b are integers. Because there probably is some a and b where this is true. There definitely is an a and b where this is true. We're talking about integers here. There exists an a and b which are integers. And I don't think that is true, because if ever you take an integer such as 2 and you add it to 3, you get another integer. So an integer plus another integer must equal an integer. And it's going to be this idea that hopefully we can use to contradict the statement. So we're going to start with 21a plus 14b, and that gives us 1. 21 and 14 both have 7 as a common factor. So I'm going to divide everything by 7 here. So we've got 3a plus 2b, and that's going to be equal to 1 over 7. Now, if a and b are both integers, here we've got an integer plus an integer, and that must equal an integer, but 1/7 is not. So this is a contradiction here. So as a and b are integers, the sum should be an integer. And unfortunately, 1/7 is not an integer. And hence, we have a contradiction. So what does that mean? We should finish off by saying there does not exist any integers a and b for which this is true. So therefore, there are no integers such that, and then I'm just going to repeat that first statement, 14 or 21, whatever it was, a plus 14b equal 1, and that's it. So that is a quick kind of crash course in proof by contradiction. Remember to start by going with the assumption of the opposite, where you assume the opposite kind of statement is true, and then you're going to contradict that to show that the original statement is therefore the true statement itself. So, and that's all we're looking at for this one. Hope that helps. If you find any questions that you want some extra help with, just post them below this video or get in touch with me. That's fine.